Hello guys, today we're going to be covering section 5.1 or really starting chapter 5, which is integrals. So, this is basically just going to be like the final chapter of the course, but chapter 5, integrals, beautiful section, love it very much. So, the first thing we need to talk about, I'm saying integral, what does that word even mean? We have to get some context. So, the first thing we want to do is try to set up a situation where we want to, come up with something new. So we're going to talk about areas and distances, and we want to solve an area problem. So, we want to find the area of a region S under the curve y equals to f of x from a to b. So we have like a function, y is equal to f of x. We have, it's going from a to b. So this is on like an interval ab. And what we care about is S, the area of S. So this will be like a region where like we have one side is going to be, x is equal to a, the other side is going to be x is equal to b, and the bottom piece is just going to be the x-axis. And, and then we have the top is going to be defined by the curve. So the fact is what we want to know is, what is the area of S? So we know like, a and b are fixed. We can figure out all this, we can figure out all the other stuff. But the thing is we don't know the curve, we don't know how to take the curve into account. So, like if this was like a square, then we could just, do length times width times height. If it was like a triangle, then it would be pretty easy. Basically anything, finding the area of an object when we have straight sides is really nice. Like shapes like triangles or rectangles, are pretty easy to use. But it's not that, simple when we have curves. We could have like any kind of curve we want. Polynomials are curved, like cosine and sine of x. We have logarithms. And if we're going to try to define our boundary like that, trying to define, one of the edges of that region to be like that, then we can't just, have a solid formula for it. There's no way for us to like if I just give you this shape, this is a curve and it'll have some area inside of it, but there is no formula that can give us that. So we have to come up with a new method to do that. And this is where integrals come from. Our goal is to find the area of S, or, find something that approximates it. So what we want to do is, approximate the area by rectangles, and then take the limit of the areas of the rectangles as we increase the number of rectangles. Take the limit of the sum of the areas. You'll kind of see what I mean. I think that seems a bit weird, but basically what we're going to be doing is, if we look at this region S, if we just say this is a rectangle with some height, say this is another rectangle with this height, another rectangle right here, and we could just keep on building these rectangles. So each of these rectangles will have some width, which we'll call delta x, and it will have some height. And we should note that the height, one of the heights of these curves always is kind of dependent on the curve. We're not going far away from it. We're not going, you're not going too far away from it. We're not, we're relatively close. We want the height to basically kind of match up to like the curve somewhat. So, if we look at, the fact that I just drew these like rectangles, like this one right here, this one, this one, this one. And if you look at the area, we still are missing a few sections. We're still missing like this section right here, this section, and we're still missing a bit. It's not a perfect, approximation. Well, I mean, you can't be a perfect approximation, well, sort of, but the thing is, it's not, it could be better, is what I'm saying. So how do we define better, or how do we make things better? Is we take we take more and more rectangles. If we let's just say I add another rectangle right here and I make it have this height, and then I just kind of keep this one the same, I would have to decrease the width of the rectangle, but I'd get a better approximation. And this is where this idea comes from, is that we want to, use rectangles to estimate the area of a parabola. You want to use, rectangles to estimate, the region where it's kind of defined by S. And typically we would say like, the area under the curve. So, let's try it with a parabola, from y is equal to x squared from 0 to 1. So the parabola is going to look kind of like this. It's just a normal shape like this. Oops. Yeah, you kind of get the idea. That's just the shape of a parabola from like 0 to 1. And, we know the area has to be between 0 and 1 because the area of something with 0 would have like 0 height. And if you look at the rectangle itself where it has like side length 1, side length 1, if you look at this whole region, then that area is 1 because it's just 1 times 1. So that kind of tells us is that as S is kind of trapped inside of that, then that tells us that, the area of S, or like the area of S, which we'll call A, is, somewhere between 0 and 1. But that's a really poor approximation. Because like if I gave you like a dice roll and I just said, you asked me like if I give you some dice, or like no, okay. If you gave me some dice, like I don't know, like a D20 or say, like a 20-sided dice. And you were like, hey, what is the probability of me rolling like a 5? And I'd be like, it's somewhere between 0 and 1. Like, that's utterly useless. I give you nothing useful. And, sometimes that might be good, but, it's pretty bad. So what we want to do is use the rectangle. So we divide S into 4 strips, 4 rectangles, and we want to approximate the area in 2 different ways. Because one of the things that was like, how can we choose the heights of the rectangles? How do you know what size rectangles to make? So we're going to cut the section, we want to approximate, we're going to cut S into 4 different shapes. So we're going to call it S1, S2, S3, S4 using rectangles. So what we're going to do is we're going to have rectangles with the same width. And we're going to use rectangles, and we're going to use the height by evaluating f of x is equal to x squared at the right endpoint of each subinterval. So this might seem weird so far, but okay, we should note the interval. So this is 0 to 1/4. So this right here has length 1/4. 1/4 to 1/2, also length 1/4. 1/2 to 3/4, length of 1/4. 3/4 to 1/4, length of 1/4. So if these were rectangles with a base of 0 to 1/4, then that would have like a rectangle with width 1/4. So that's kind of where we get our first thing from. So this is like, let's just say 1/2, 3/4, 1/4. So then our first rectangle would be like split on, like we define that the size of rectangles to be like these. Now we're not done yet because, what I did right there was just split this into the section. So this was S4, S3, S2, S1. And now we split up S into the sections going from, each of the subintervals. So there we're going to evaluate, we can get the height, so the height of each rectangle to equal to the right endpoint of, of each subinterval, and we're going to evaluate f of x there. So evaluating f of x, which is equal to x squared at the right endpoints of each subinterval. So what does that look like? So the right endpoints would be like if we, like the subinterval from 0 to 1/4. It's going to be going from 0 to 1/4. So this section right here. And we want the height to be the right endpoint. So if you look at the right endpoint, that's going to be 1/4. And that whatever that curve is there, that's going to be our height. So that's going to be our rectangle right there. And likewise for the next one, it's going to be 1/4 to 1/2. We choose the right endpoint. So whatever, the function's there, that's going to be our height. So this is our rectangle. And likewise, we keep on doing this. And then we could just actually find out the areas of these rectangles. So if you look at each rectangle, it's going to have like the first one right here will have a width of 1/4, and it'll have a height of f of 1/4, because 1/4 is our right endpoint, and that's what we plugged in to find the height. And this one right here, S2, well, the area of the rectangle for S2, again, we said that, we had the width of 1/4, and we said where it's going to be like, it's going to have a height at the endpoint. So the right endpoint of this one, was 1/4 to 1/2, so it's going to be 1/2. So f of 1/4 times 1/2. That's going to be the area of that rectangle. And this right here isn't so bad, but you just have to understand that we have to define the rectangle somewhere. The rectangles are going to be of equal width, And what we're going to do is, like, when we put these rectangles into an xy plane, they need to have, the width has to be defined somewhere, and the width is going to be these subintervals. And when we choose the heights, we choose the heights to be some point on the subinterval, but specifically we're doing the right endpoints. So each rectangle is going to have some width of 1/4. Oops. The heights are going to be 1/4 squared, 1/2 squared, 3/4 squared, plus 1 squared. So this is just 1 over 1/4, f of like 1 over f of 1/2, f of 3/4, and f of 1. Because those are just like the function values there. So try not to think about them as squareds. The fact that they're squared doesn't really matter. The only thing is that they're just numbers, and those numbers correspond to those heights. So we're going to let R4 to be the sum of the areas of the rectangle. So R is going to be R stands for the right endpoint, and 4 means the number of rectangles. So we're going to take up, we're going to add the sum, we're going to add the area of all the rectangles. This is going to be 1/4. So this is like the width times our height, which was, f of 1/4, which is, remember that our f was x squared, so it'd be 1/4 squared. And we just do that for the rest of them too. So it'd be the first rectangle, this one, plus the area of the second rectangle, this one, plus the area of the third rectangle, and so on. And we add them all up, and we get, it's going to be equal to 0.46875. But, if we look at this, what can we determine based off the graph? What kind of approximation is this? So, if we look, we chose the right endpoint, this is an over approximation. This is too much. This right here, this is the region, it's going to be too much. This right here, too much. This right here is too much. So that in itself gives us a problem. We actually overcounted, but that's still useful. So this is an over approximation, but the area of A, which will of S, is going to be smaller than R4 though. So our total area, whatever area under that curve will be less than 0.46875. So, last time we got between 0 and 1, not very good, could be a lot better, but this one's actually much better. Now we're going to have the areas going to be less than, 0.46875, which is a lot more specific. So, we note that we don't have a bottom piece yet. Technically we still have 0, but whatever, that could be better too. But, instead we can, still try to use, we can still do an under approximation. So this is where we're going to use the left endpoints. And I want to clarify that the right and left endpoints do not give you under or over approximations respectively. It only depends on the function. So if the function was decreasing, then it'd be vice versa. But really it just depends on where the endpoint matches up. And in each case here, the endpoint is just the highest point on each subinterval because it's an increasing function. But again, that doesn't necessarily have to have a correlation. So just be careful of that. So now we're going to use the left endpoints. So remember the intervals were 0 to 1/4, 1/4, 1/4, 1/2, 1/2 to 3/4, and 3/4 to 1. So the new numbers that we're going to choose is going to be 0. Whoops. 0. Oh, shit. It's going to be, 0 is going to be our left endpoint, 1/4 is going to be our next endpoint, and 1/2 is going to be the next endpoint, and then 3/4. Because, when we approximate something, you want to use some information about the thing you're approximating. If you don't have any information, you have any guess, if you never, sampled, is what you can also say, then you don't really have, any information that's useful that allows you to approximate it. So what we need to do is, and that's why we can choose, the left or the right endpoints, because the left or right endpoints are where we choose to sample. Where are we deciding to get the information from? So in this case, we're choosing the left endpoints to approximate. So what this will be, we want to do the sum of the rectangles. So the first one is going to go from, it's going to have width from 0 to 1/4. That's going to be at the base. But it's going to have a height of 0, so it's just going to be 0. Because the only thing is, this is f of x is equal to x squared. It was f of 0. Which is just, 0 squared, which is just 0. So let me just kind of indicate the left endpoints were 0, 1/4, 1/2, 3/4. So then the next one's going to go from like 1/4 to 1/2, but now the left endpoint is going to be here. So now that's going to be our first rectangle. Well, it's going to be our second rectangle actually. Our first one actually has like no height to it. And then we're going to do the same thing for the third one. It's going to be, f of 1/2 is going to be the height. So that's going to be our next rectangle. And then lastly, for our last endpoint 3/4, it's going to be this point right here. That's going to be our height. So then these are our rectangles right here. So, the first one was going to be like the width was 1/4. All the widths are 1/4. And then the function values are the height. The points where you decide to, the points where you decide to sample the function is going to be, 0 squared, 1/4 squared, 1/2 squared, and 3/4 squared. And remember that these aren't, numbers squared specifically. It's more that this is f of 3/4, and this was our height. So, we add them all up together, and what we get is 0.21875. So this actually is an under approximation. If we look at, the curve, we're missing this much area, we're missing this area right here, we're missing this area, and we're missing this area as well. So this tells us that, we didn't account for everything. So again, under approximation. So this is but this still tells us a bound. We still have now finer information about, the area under, f of x, under the curve. So we know that the lower approximation was 0.28175, and we said the upper approximation was 0.46875. So that tells us that the area is between these two values. So, the first thing we noticed was between 0 and 1, which was like helpful, but, well, it wasn't, it was like a poor approximation, it really wasn't helpful. But now using these rectangles, we actually begin to approximate the area a bit better. And, this gives us some bounds. So if you want to get better bounds, or if we want to get a better approximation of the actual area, all we have to do is, take more strips. And we get better and better approximations. So like if we look at this one right here, assuming this is an upper approximation, we're using the right endpoints. It may not be clear. What the heck? Okay. Sorry, that was weird. I didn't want to erase. It may not be clear, but this area right here, the fact that we use the right endpoints now, it's actually smaller than the area, the overestimate we had before. And the actual area we get for all these rectangles, and we add them all up, we get 0.3984375 or whatever. And likewise, whenever we do it for the, the left endpoints, which will give us the under approximation, we get, again, something like this. We get an under approximation, but that error is definitely not as big as what we have right there. So, and we got for that 0.2734. Is that right? I don't think that's right. Weird. Sorry, I noticed something. But typically what happens is whenever you increase the number of rectangles, you get better and better approximations. And that's kind of what happens, if you think about if you're measuring something, if you're trying to measure the length of a table. If you could only do it in meter sticks, if you can break it down any further, if you just have a stick that you just know is a meter long, then you can be okay, it's either it's somewhere between 1 and 2 meters. But let's just say you take that stick and now you mark a 1/2 meter on it. And then you can just say, and now you can basically get a better approximation for the length. So now you can go from 1 meter to 1.5 meters to 2.5 meters. And now you can go from 2 to 2.5. Now you have an extra thing to work with, an extra unit. And each time you add another, mark on that, stick that kind of tells you what a length is, whenever you get smaller and smaller lengths, you get better and better approximations. You can get a more an approximation that will actually give you the length of a table. So, and that's the idea, you add more and more rectangles and the error should get smaller and smaller. So, if we continue to split the interval with, 1,000 strips, the area would lie between 0.3328 whatever, and the upper one would be 0.3338335 or whatever. So that gives us an area so a good estimate of the area, would just be like you could add them together, divide by 2 or whatever, but you really get like 0.333335, which is actually a really good estimate, honestly. And, you might have to you do 1,000 rectangles, but the idea is, we're doing this mathematically. We don't care about calculations so much. We want this to work, is the idea. So we're going to take what we just did, using these rectangles and using rectangles to approximate, the area of a curve or the area under a curve. And we're going to generalize that and try to get it more rigorous. We're going to make the setup. So, whenever we cut up the subintervals, how did we get, 0 to 1/4, 1/4 to 1/2? We did mention that the width was the same, but how do we figure out the width? So let's try a more general setup. Let's say, we have curve y is equal to f of x. It's going to be going from A to B. And, we're going to cut, the section into, many different pieces. So it's going to have, x1, x2, all the way up to xi plus 1, all the way up to xn minus 1 to b. So this is what we're going to get when we take a, b, the whole interval we want to, kind of find the area over. And we're going to cut it into n pieces. And this is where we get, basically n plus 1 points. And so what this gives us is either n right endpoints, or n, left endpoints. But the point is that, the endpoints are going to be corresponding to these values right here. And when we do that, we're going to say, we have subintervals that are going to go from x0 is going to equal to a, and we have x1, and then we'll have which will be smaller than x2, and so on. We'll go to xn minus 1, which will be this point right here, which would be less than, xn, which would be equal to b. So this may seem weird, but the idea is, imagine if you just cut a piece of wood, let's just say you have a piece of wood, you call one side of it 0, call the other side of it, B, I guess. And if you want to cut it into, pieces, then, each cut, you could call the first cut x1, call the second cut x2, and so on. And, all these inequalities really mean is just saying, okay, one cut goes from is a bit more left than the other. And, so far that's kind of weird. But the idea is, we want to define our rectangles nicely. So we split up the curve, the area under the curve, all this was just the whole region was S. The whole, area under the curve was S. Well, no, the region was called S. The area was A. Sorry, it's the notation for this, not the notation, but trying to be precise is weird, but typically we just say is the area under the curve, but actually including this area too. So when we cut the interval into n different pieces, we have n subintervals, and we basically get n strips that have equal width. Well, we want to divide the region S into n strips that have equal width, and we want to use that to approximate it and that's how we're going to find the rectangles. So we're going to say the width of the interval, which is going to be AB. I think what the best idea would just be B minus A. Because, you want the distance from 0 to 1 to just be 1. So the distance between A and B should just be B minus A. So you take the length, you cut it into n different pieces. So the width, that should be width of each strip should be, B minus A, the total length, cut into n equal pieces. So that each rectangle will have width of delta x to equal b minus a divided by n. So that's our width. So we're going to divide, keeping that in mind, we're going to divide AB into n subintervals. And what I said before, we're going to use those x0s, x1s, x2, xi plus 1, xn minus 1 to xn. This is just a very general way of writing, these subintervals. So the first thing is, we want to write it like this, where, again, the right endpoint of 1 is going to be the left endpoint of another, because this is like x1, this is also x1. So the first point, x0, that's going to be our A. The last point, xn, that's going to be our B. And the right endpoints are the subintervals. So the fact that we know A, then we want to find, x1. The once we know x1, we can use that at x2. And then we figure out all these subintervals. So again, we said the subintervals all have equal width. We want them to have equal width, which was delta x is equal to b minus a divided by n. We're just going to keep that as delta x right now, because that's dependent on certain situations, but we're going to keep that as delta x. So x1, we have this length is going to be delta x, so it should be a plus delta x, which is what we expect. If you cut along that piece of wood that you had, and you go from you cut it into n pieces of equal widths or equal lengths, then when you start from the very base, then how far along you cut, which is our delta x, you would want that x1 to be there. And then likely, because you cut it into equal pieces, then you would want to go the same distance you just did to get to the first cut, to get to the second cut. So this would be, a plus delta x, where delta x is our width. And then you would do, the first cut plus the distance, plus the width. But what is x1 again? x1 we just had was a plus delta x. So really we just get a plus 2 delta x. And that's actually, helpful. This is how we're going to define it. Because it doesn't matter if you're the same width from the first cut. What matters is you're actually that in many cuts, in many widths away from that cut. So, x3 will be equal to a plus 3 delta x, and xi will be a plus I delta x. And remember, I right here is just going to be some number between 1 to 2 to 3 to some number to n. And the reason for that, the reason for I is because I is just a placeholder for any of these numbers right here. Any number that is between 1 and n. So we can approximate the ith strip of a rectangle with delta x and height of f of x sub I. So again, f of xi, if we're doing the right endpoints would be xi. And so we're going to be using that as our height. And by ith strip, by rectangle, the ith strip, approximate, the ith strip by a rectangle with delta x and height f of xi. All that really means is again, the ith strip, the only thing it means is we're just choosing an arbitrary rectangle without being specific. That's all that means. That's what the i's mean. We want to be general without needing to be specific. So the area of the ith rectangle is going to be, f of xi times delta x. So this is our width and this is our height. So, if you want to figure out Rn, which is again the sum of the rectangles with equal width with the right endpoints. So remember, n rectangles with right endpoints. That's going to be the first rectangle plus the second rectangle plus all the other rectangles plus the last one. So this was f of xn delta x. And, based off our intuition, and, this can also be proven, that when we take more and more strips, we get better and better approximations. So what does that mean in terms of actual problem in terms of all this? Well, if you look at the graph, if you look at the area of okay. So what does this mean? Well, let's actually talk about it in terms of the definition. So the definition, or will be the area of A. So we're the area that we should care about. So the area of A of the region S that lies under the graph of the continuous function f. It doesn't necessarily need to be continuous, but continuity is basically going to be a nice assumption that we're just going to assume. So, again, that's basically just saying, the area under the curve is going to be the limit of the sum of the areas of approximating rectangles. So basically what's saying is, if we take this, as n goes to infinity, take the number of strips to go to infinity, then we get that A will be equal to the limit. So that basically says we're going to get more and more rectangles, but the width has to get smaller, but that's okay. We're going to get better and better approximations. So Rn is going to equal to, like what we just had before, was f of x1 times delta x all the way up to f of xn delta x. And we write that in terms of a sum. It's going to be the sum from I equals 1 to n of f of xi delta x. And remember that this I doesn't mean anything. It's just a placeholder. And it's a placeholder because everything, if you look at x1 delta x, if you look at x2 delta x and xn delta x, the only difference between them is that we have an, is like this point right here. Here we have a 1, here we have a 2, and here we have an n. So if you want to write it in we say sigma notation or sum notation, we just take the common thing between them, or we can just put an I there. Because it will go from, this was the way you represent the sum of all numbers going from I equals to 1 to n. So the first thing you would plug in would be I is equal to 1, and you get that. And the next thing you would plug in would be I is equal to 2, and you wouldn't get that. So this represents the sum of all things with, of all the form, f of x I delta x, where I is between, 1 and n. So, that right there is really powerful, and that's basically the whole idea behind integrals, is that we can take these rectangles, take a infinite number of rectangles. Technically you can't do that, but take as we get more and more rectangles, get cut into more and more strips, then we get that area. And also the left endpoints get the same result, but we'll kind of talk about that more in the next section. But in fact, we could really talk about any xi, or in the ith subinterval, xi minus 1 to xi, to find the height of the rectangle. So we can call the numbers x1 star, x2 star, x3 star, all the way up to xn star. We call those numbers sample points. Because again, I kind of told you, it doesn't really matter, it doesn't really matter where you choose to sample. The fact is you have to sample. So if we're just going to look at this point right here, if we look at this interval, whatever this one is, I could choose the height to be, the left endpoint. I could choose the height to be the right endpoint. But anything in between also works. There's no reason for it not to work. So, and that's that's the idea. We can choose any point really. It doesn't necessarily have to be the left or the right endpoints, but the left and right endpoints are just very nice, and then we just like to use them. And what I wrote right here is they're called Riemann sums. So the Riemann sums are when you don't specify, and you just let them be random. You just let them be some points in the interval. So xi star. So instead of having, this right here, which specifies the right endpoints, it would just be xi star. And then this right there, of that form, would be a Riemann sum. But, again, we'll get that to the next one. But, we can also form they're called the upper and lower sums by choosing the sample points. The points that we want to use on F to approximate it, to find, the height of the rectangles. We can choose that so that f of xi star is either the maximum or the minimum value of f on the ith interval. Because it's we could choose the highest point of f on the interval, or we could choose the lowest. It doesn't matter. So but specifically when we talk about the upper sums, we always specify the max. If you say the lower sums, you always specify the lower. We always talk about the minimum. So if we look right here, oops. The lower sums, our interval is going to go from this. This is going to be our interval right here. Our lowest point was going to be this one. If we go from here to here, our lowest point will be this one. Out of all the points right there, and so on. And as you see, each time we get rectangles that are below the curve. They touch the curve, but they always below. And it's not very clear in this case, but it's not always the case that the lowest point or the maximum point. We don't necessarily always have to sample, the left or the right endpoint. The whole point of the sample points is that we could choose this point to be a rectangle, and that would be okay. We could still get that behavior. We don't necessarily need to do this point or this point. We could choose these points instead. And But those does not necessarily guarantee a over approximation or under approximation, which is why we sometimes specify. And like the upper approximations, well, the upper sums, we choose, if you look at this interval right here, we choose the max. So this would be the max. So this rectangle would be greater than that, the area of that strip. And, we can do that for the rest of the points as well. And you should note that here, this was the left endpoints. Well, the right endpoints were the max. Here, the left endpoints are the max. And right here, the max was actually like, it may not look like it, but what was happening was that the function was looking like this. And the region was looking like this, where a max was like, some point in between the endpoints. So in this case, the upper sum gave us an over approximation, the lower gave us an under approximation, and so on. So the main idea I want you to keep away from this section is not that, we're doing anything tricky. We're just taking rectangles, we're approximating them, and, we have the case that more and more rectangles just give you more and, better and better approximations. But thank you guys for watching. I hope you guys enjoyed at least learning about the sums and the basis of integration. But like, comment, and subscribe. Peace out.